Good day. Welcome to this episode in which we are going to look at problems which were set by the South African Mathematics Foundation in 2024. And these particular problems were part of the South African Maths Olympiad, the round 3 of the junior competition. So without much further ado, I will go straight to the problems in question. Okay, sorry, there was a little struggle there. Uh, the very first question that we are going to look at is this one. It was a very popular kind of a game that people played a couple of years ago, many years ago, I think, where they had um, where four numbers were given, and the idea was to create the number 24 from these four numbers using the operations of addition, subtraction, multiplication, and division. Um, like in this particular problem, we have to use the numbers 2, 3/8, 8, and a quarter to eventually get to the number 24. All right, there is no particular algorithm or particular way of doing these things. Um, one has to foresee where you are going to land at, and you try to land at 24. And somehow you move through the numbers to try to see whether you can get to that. In this particular case, it wasn't very difficult for me because I saw 8 and 3/8 um, in this in these amongst these numbers. So I knew immediately if I multiply these two numbers, I get 3. Now from 3, can I get to 24? So let's just write that down. So we have 8 and 3/8. When you multiply them, you get 24. Okay, so 8 times 3/8 is 3. All right. Now, you have to use all four numbers. So I've used those two numbers. So the next thing is I see a quarter. There are four quarters in one. So in 3, there are 12. And from 12, I can get to 24. So that helps me quite a bit. So I take 3 and I divide it by a quarter. That's the answer I got there. And there I get 12. Okay, either you can say 4 quarters in 1, and therefore there are 12 quarters in 3, or you can use the usual method to divide. You multiply by the inverse, or you turn it around and you'll get 12 again. Okay, and then finally, 12 to get to 24, you can get to that very quickly now. It's 12 times 2. So you probably would have tried out various kinds of things before coming to this answer, but that is how this problem is. It teaches people to do a lot of calculations mentally. All right, so the next problem is again a number problem. It says here in the 3 by 3 grid below, you can see the grid at the bottom, and the numbers 1 to 9 are placed in this grid, in these 9 numbers. Okay, let me just see whether I can get to this. Oh, okay, it's not working. let me just use my normal pen. So you need to put 9 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9. But we don't know in what arrangements they are. And no number should be repeated. So you have to write all 9 numbers. And these numbers on the side say that these are the product of these 3 numbers here is 15. So if you multiply those three, you get 15. Likewise, the second row, if you multiply them, you get 224. And the third row. And in the columns, the first column, if you multiply these numbers, you should get 72. And likewise, if you multiply these, you get 40 and so on. So the question is, what are these numbers? All right, now the trick here is that you're looking for a factor. Let's take 15. You're looking for a factor here. These will be the factors, but that factor will also be in the column in which that number appears. Now, you see the factors of, if I look at 15 and if I look at 40, they do have a common factor, namely 5. So it looks very strongly that 5 is here in the same column as the row in which this thing appears, because then 5 would be a factor of 15. It's also a factor of 40. And 5 is allowed because 5 times 3 is 15 and 3 is just a single digit, you see. So you got 5 here and the other number here. Right, so 5 goes into 40, exactly. And the remaining factor is 8. Okay, so now we have a situation where these 2 numbers here multiplied, product comes to 8, and likewise, no. So these 2 numbers come to 8. And these, if you multiply these 2 numbers, you're going to get 3. All right, so we can't get to too much there, but now we look, if you think carefully, you'll see amongst the numbers from 1 to 9, there is the number 7. That's a prime number, okay? And let's see whether 7, what does it go into? If you check it out, you'll see this is 7 times 32. 7 goes into this. You can divide it by 7, and even this too, this is 7 times 18. All right, so it looks as if, well, certainly the row, this row here will contain 7, this column here will contain 7, so it has to be 7, has to be here. All right, now let's have a look at these numbers here. Now, you know that these 2 numbers multiply to 18. I've got 126, 7 times 18. Okay, let's have a look at this number here. Here, what are the factors of 18? It could be 1 and 18. That's not allowed because then you'll have to put 18 inside here. It could be 2 and 9, but you can neither put 2 or 9 here because that has to be a factor of 15. So the next only one you got is 3 and 6. Right? So if you try 6, 6 can't go in here. 6 is not a factor. But 3 certainly goes into this, and 3 goes into 18 as well. Right? So you can put, this is 3 times 6 to give you 18, and here you will have 3 times 5 times 1 to give you 15. So we're getting there. So like that now you can go on to fill this entire square. Like for instance now, these 2 numbers will have to multiply to 32, while these 2 numbers multiply to get to 8. 5 times 8 is 40. So how are you going to do that? So you can't put 8 here because then you're going to have 1 here, and we already have a 1. So these 2 numbers multiply to get 8. So we can put 4 here or 2 here. But if you put 2 here, then these 2 multiply to get 32. You have to have 16 here. So the only number that you could put 4 is 4, and 4 times 8 is 32. And here, 5 times 4 is 20, and 2 goes in here, and finally you have a 9 here. 1 times 8 is 8, 8 times 9 is 72. So this involves a certain amount of logic to remember that you're looking for a common factor, a factor which is in the row and also in the column. So if you understand that, then it's not that difficult. Okay, bearing in mind that all these numbers are digits. Right, so now that takes us to the next problem. So the next problem says the square ABCD, that's the large square here. The square, it contains three squares. You can see the picture, red, yellow, and blue. And it says here that the red square has got area 16. So immediately, without reading much of that, the area of the red square is 16, then it means that the sides are 4. So I can put a 4 here and I can put a 4 here. Okay. All right, so it says a blue square of area, the blue square has area 64. So in other words, you'll have to have 8 times 8 is 64. The area of a square is side squared. So this is 8. And a yellow square, okay, they don't tell you anything about the yellow square, but they say the gray area, this entire gray area is 32. This entire gray area. And then calculate the area of the yellow square. All right, so we don't know the area of the yellow square. So the way to start this thing is say, okay, suppose you say x is the side of the yellow square, and you need to find the area of the yellow square. So the question is, what is the area of the yellow square if the side is x? It is x times x, side squared. That's the area of a square. So we need to find out what is x squared. That is the goal. Okay, to do that, we need to find x. All right, now how do you do that? Well, we know this area here is 32, but it's made up of all kinds of, it's a funny shape. So what we have to do is try to break this thing up into shapes that we can understand. And the way to do that is to create 3 rectangles. Because I can complete this rectangle here like that. And then this one. So now I have 3 rectangles. And the area 232 is actually equal to the sum of the areas of these 3 rectangles. So I know that 232 is equal to the sum of 3 numbers, and these numbers are areas of rectangles. Now, can we calculate the areas of these rectangles? All right, now that takes a little while because we need to know all these different lengths here to calculate these areas. So let's do that. We already know that the side of the square is x plus 12 because on one side I've got x, 4, and 8. So therefore, all the large one is a square. It says here ABCD is a square. So all the sides have got x plus 12. So if this is 4, this has to be x plus 8 to get x plus 12. And if this is 8, this has to be x plus 4. All right? So that should allow me now to do the calculations. Because this side here is x and this is 4 also. So this is a rectangle, so all the opposite sides are the same. So this area here is 4 into x plus 8. Area of rectangle is length times breadth. This area here is, okay, so you need to know what this is. Okay, now that requires a little bit of thought we know that the entire side is x plus 12, and this is x. So that's the side here is x plus 12, the entire side, minus x, and that gives you 12. See? Now you can get the entire side is x plus 12, you see? All right, so this area here, the length is 12 and the breadth is x, so the area is x into x times 12, which is 12x. And here it's 8 into x plus 4. So the entire area is the sum of these three areas. All right, so I'm going to write this thing down. This is 4 into x plus 8. That's the first rectangle area. The next rectangle area is 12x. And the third one is 8 into x plus 4. And now we have an equation with one unknown. All right? And whenever I have an equation, the whole idea in mathematics is to work towards equations. And this particular problem leads to this equation. And usually I'm quite happy whenever I see an equation. Right. So if you expand this, you get 4x plus 32 plus 12x. 8 times x is 8x. 8 times 4 is 32. If you bring all the x's to one side, you got three of them, 4, 12, and 8. 16 plus 8 is 24. So it's minus 24x because you have 24x on this side. You bring it to the other side, it changes sign. And here you got 32 plus 32, which is 64. And then you have 64 minus 232. All right, I'm not going to go into much with that. It works out, it turns out that x is 7. From this point onwards, it's easy. All right, so that is how we do solve this problem. The only difficulty was you got a gray area. You can't find the gray area. It's got a very irregular shape, but you can break it up into shapes whose areas you know. And that was the important thing. I know the area of a rectangle, so I broke it up into 3 rectangles. Okay.
Mm. Mm.
We continue with the problem question, which is question 4. Question 4 says the following: an Egyptian fraction is a finite sum of distinct unit fractions. So what are unit fractions? A unit fraction is a fraction with denominator 1 or numerator 1, maybe like 1 over 5 and 1 over 9 and so on. As long as the numerator is 1, then it is called a unit fraction. Okay, the question is, write 20 over 24 as Egyptian fractions. In other words, write it as a sum in 3 different ways. So you have to write this as a sum of numbers in 3 different ways. So what is really the problem? The problem is to write 20 over 24 as 1 over something plus 1 over something plus 1 over something and so on. The Egyptian sum, it could be, it's a finite sum. In other words, it could be sum of two numbers or three numbers or whatever. Okay, so these are the problem is, what are these denominators? And it seems that there are three different ways at least in which you can write this thing in this form. All right, now that really seems to be a difficult problem. How are you going to find these numbers? Let's just have a look at a sum of two Egyptian fractions. So you got, say, 1 over, we'll call it A1 plus 1 over A2. This is A. All right, and let's see what happens here. When you add two Egyptian fractions, your denominator is A1, A2. It's actually the LCM, but it doesn't really matter. A1, A2. And the numerator is A1 goes into this A2 times A2 plus A1. Now, if you analyze this, you will see that your denominator, the sum of two unit fractions, is a single fraction with the denominator. But the important thing is that this thing here is a factor of the denominator. And this is also a factor of the denominator. Right? The A2 times something, namely A1, is this. If you add three factors, you'll have the same kind of a thing. Right? You'll have that each one is a numerator is, I mean, each number which appears in the numerator I'm not going to do this thing, but you'll see that there are three numbers, and each of these is a factor of that. Okay, so that tells me that the problem is to write 20 over 24 as a sum of numbers. Right? The denominator we already know is 24. So it will be 24, and this is a sum of various numbers. But each one of these is a factor of 24. But now we know that the numerator is 20. So in other words, these sums actually, they add up to 20. Okay, so after having analyzed that problem, then we ask ourselves, now let's see what's going on. You want the factors of 24 play an important role here. So let's look at the factors of 24. They're 1 and 24, 2 and 12, 3 and 8, 4 and 6. Okay, those are all the factors. And now you want to write 20 over 24 in this form. So you need to have three numbers here which add up to more, maybe two numbers or three numbers which add up to 20. Right? The problem is to find three factors that sum or that add three or more, or well, need not be three. Find factors that sum to 20. And if you try to work out two factors, you will get 12 and 8. So there are two factors which add up to 20. So let's write the thing down, 20 over 24. This is equal to 12 plus 8 over 24. And now, whenever you have a object like this, if you have A plus B over C, you can write it as A over C plus B over C. So if you simplify this, you'll get exactly that. So you can break it up as 12 over 24 plus 8 over 24. And because the 12 is a factor of 24, it factorizes nicely. They cancel. And there it is. So you write 20 over 24 as a sum of two unit fractions. Now those are the only ones which add up, only two which add up to 20. All right, but we need to get two more because they say in three different ways. So now we have to look at three numbers which add up to 24, or 20 at least. A quick inspection, if I put one of the numbers as 2, then I've got 18. And oh yeah, I have 12 and 6 add up to 18. So you're going to have 2, 12, and 6. Or you could put 20 over 24. If one of the numbers is 2, is there any other way you can add two other numbers to get to 18? No. All right. So then we can try. Uh, so let's try 3. So you have 3 and 17. Are the two numbers which add up to 17 here? I can't see two numbers which are adding up to 17. So we can try 4. Are the two numbers here which add up to 16? Um, 12 and 4 we can have, but you're not supposed to repeat because they say different here, see? So for 4, to get 16, no, it doesn't work. So if we try, um, you want, yeah, you can wear 2, 4, 12. No, 2, 6. What about 2, 6? No, we already had 2, 6. 2, 8 doesn't work. Okay. So the next one is 4. 4, I can't see it straight away. 4, 8, 8, 4, 6. Uh, maybe 1 and 23. Maybe you need 3 or 4 numbers. So you can 1 and you could put 23, 12, 8, and 3. No, uh, you need to get 19. So uh, that doesn't work as well. Anyway, I'm sorry, I can't seem to get the, just hold on. Yeah, you can. See, you need to have 2 and 18. So what we can do is you need to have 4 numbers which add up to 18. So if I put 2 here, I need 3 more numbers. 3 numbers don't work. So if I try 4 numbers, are there 3 numbers which add up to 18? Yes, it's 8, 4, and 6. 4, 6, 8. All right, so that gives you the 3 numbers that you're looking for. 2 over 24 plus 12 over 24 plus 6 over 24. And here you have 2 over 24, so 1 over 12, 4 over 24, 1 over 20, 6 over 24. So there are 3 ways, at least, in which you can get 20 over 24. All right, so, sorry, I couldn't find the last one quickly there. Okay, let's get on to the next problem. The next problem says the following. 8 towns are connected according to the map shown. Now, actually, the original map was the one that we are looking at on the right-hand side here. I've drawn this one. We'll come to that just now. So there are 8 towns. It's Abington, Bromley, and all these different names. And if you think about why they chose all these funny names, maybe there are some of these towns are there in England. But the letters, if you just take the first letters, A for Abington, B for Bromley, then you will see I've got A, B, C, D, E, F, G, H. Right. And I put them into a much neater situation like this. So these are the 8 towns, the 4 here, the 3 here, and the 1 here. All right. I'll put it into a neater diagram. It's exactly the same thing, but it looks easier to work it out from here. Okay, now, so what about these 8 towns? They say there are 4 bus routes. The route 1 is 17 kilometers long. Now, what is route 1? Route 1 starts from C. C, D, E, F, G, H, C. C, D, E, F, G, H, C. All right, so it's this rectangle here. Okay. So this is route 1. Oh, wait a minute. This is route 2. This rectangle is route 2. No, that's right. That's right. The rectangle is route 1. Okay, the next one is 12 kilometers. It's a smaller one. It starts from A, B, C, F, G, H, A. A, B, C, F, G, H, A. So these are all connected, as you can see, right, by bus. So it's the second route is this rectangle here. The first route, that rectangle. And they also tell you that route 3, that's the largest one, is 20 kilometers long. And if you analyze this, you will see it's a full boundary. And that is 20 kilometers long. So the full boundary is 20 kilometers long. This part here is 12, and this long rectangle is 17. So you got 20, 12, and 17. Right. Looks rather complicated. They say route 4 is CFGHC. So it's CFGHC. I'll put this in dotted lines. Right? The reason is they say how many kilometers are there in route 4. Right? So what is this route here? The full distance that the bus has to travel along this. Okay, so it looks very complicated because there's so many unknowns here, right? And normally people will work with all these unknowns and it can be quite complicated. But I found a very nice way of handling this problem. And it's here. So what we are doing here is, so this is the original problem. Now, if you break root this one here, the which we said is root 3. Root 3 is the entire thing. So what I've done is I've broken up into two pieces, that, and this last piece here. So you can see that these two together, they add up to root 3. All right. Now, when you add this and this, what happens here is that you are actually adding this piece, which was in root 2, and we're adding this piece here, which is in root 3. So if you add root 1 and root 3, you will have all these together with the red lines. Right. But we don't want that. We only want the black lines. So the actual black line is the same as, you have to remove the red lines. That's what I've done here to get the black line. So in short, what we are saying is that root 3, let me just go back to my black ink. Root 3, right? Oh, okay, we don't know this one here. The root 4. That's the unknown. Right. So what happens is that if you take root 1 plus root 2, let's just remove this one. If you take root 1 plus root 2, you're going to add these red lines as well. But if you remove that, those 3 red lines, then you will get exactly the full boundary, right? So you have only the black lines. So you have to remove the red lines, which is R4. You have to take that out, and then you land with the full boundary, which is R3. This is the unknown. R4 is unknown. So therefore, you can make this the subject. It's R1 plus R2 minus R3. So you get the answer quite quickly. It's 12 plus 17 minus 20. Okay, as you can see, this requires a certain amount of intuition and observing that the one that you're looking for is really the extra that you are adding when you add R1 and R2. So once you realize that, then the problem is not that difficult. Okay, so let's just get on to the next problem. Now, what does this problem say? This problem says the following. You got the letters of the alphabet A, I, M, R, T, X. They're actually in alphabetical order here. A comes before I, for M, R, T, X, right? They can be arranged in 720 ways. So let me talk about that now. How do you know that it can be arranged in 720 ways? Okay, suppose we arrange, just say AIM, right? Now, I look at all the possible ways in which I can write AIM. A, AIM, let's put A in the front, then you get MI. So if I put A in the front, I get those two. If I put I in the front, then I get AM, and you get MA. And if I put M in the front, then I have AI and IA. So there are 6 different ways, as you can count, in which these can be arranged. So AIM can be arranged in 6 different ways. Right. Now, actually, when you think about it, where did the 6 come from? The A can be chosen, the first letter can be chosen in 3 ways. Right? That the A, I, M. So once I choose the first letter, which is in 3 ways, I'd like to put it in a thing like this. Right. Then the second letter, once you choose the first letter, the second letter can be chosen in only 2 ways. It can be I or M. So the first 2 letters, each one, for each of the first choice of the first letter, I have 2 choices of the second. That's what I've got here. 2 here, 2 here, and 2 here. Right? So therefore, the first 2 letters can be chosen in 3 times 2 ways. But then once you choose the first 2 letters, the last one, there's only 1 left. So that will be, there's only 1 way in which you can choose that. So the 6 is actually 3 times 2 times 1. Or if you like to put it in ascending order, it's 1 times 2 times 3. Right. So there are 1 times 2 times 3 ways in which you can arrange 3 letters. But if I put 4 letters, suppose I had R, A, I, M. Right? Then what happens is, if I've got 4 letters, R, A, I, and M, then for R, the ones which start with R has got 6. Because all the letters in AIM can be arranged. Likewise, the one that starts with A has also got 6. But then the 6 will be the RIM. And the I is 6 and M is 6. So the total number of arrangements you have for RAIM is 6 plus 6 plus 6 plus 6, which is 6 times, which is 4 times 6. So here, the number of arrangements of RAA and 4, in other words, 4 objects. Doesn't really matter what these objects are, right? RAIM, we are using those letters here, is actually 4 times 6, which is 4 times 3 times 2 times 1. Right? So you have, if you have 3 letters, it's 1 times 2 times 3. 4 letters is 1 times 2 times 3 times 4. And if you keep doing it like this, you will see, if you had 5 letters, you'll have 1 times 2 times 3 times 5. Now this is what we normally write as 3 factorial, 4 factorial. You use the word factorial for this, and I'm sure you would have come across this word. 3 factorial, we write this in a short way as 3 with the exclamation mark. So that's how you get 6. If you got 6 objects here, it's 1 times 3 times 2 times 3 times 4 times 5 times 6. When you multiply those numbers, you will get 720 exactly. See, I got here 720 is 6 factorial. Okay, now why are we doing all this? It's because what we are doing is we want to arrange all these 6 letters in alphabetical order and number them from 1 to 720. Right? The question is, which number would be assigned matrix, matrix? Okay, looks like a difficult problem. So you're arranging all these words here, the so-called words, in alphabetical order. So the very first word here you will have is A. As I said, these are already in alphabetical order. the AIMRTX, that is word number 1. Okay? It's the very first word. And then you'll have all the other words which begin with A. Now, how many such words are there? All right. Then you have to look at, they all start with A, so you have to look at all the possible arrangements of IMRTX, right? All possible arrangements, and they will be the ones that come after A. How many arrangements are there here? Now, here you've got 5 symbols, so it's the number of ways in which you can arrange that is 1 times 2 times 3 times 4 times 5. If you calculate that, you get 120. So the 120 words which begin with A. Right. So once you exhaust A, then you go to the next letter, which is I. Right. And again, there is another 120 which begin with I. The 120 which begin with A. Right? So there are another 120 which begins with I. And when you finish that, only then do you get onto M. And that's where we want to be, because we want to know what position does that word occupy. Now, if you look at the 240 have gone before M, and the 241st word starts with M, and here you have to put all the remaining letters in alphabetical order. So you put M here, you'll have A, I, R, T, X. That's the order. M. Then you have A, I, R, T, X. So the very, very first one, this is the 241st number. Now we need to get to that one. Okay, so how do you get to that? Well, MA is fine, but now, or MAI, okay, so what comes after this? So you'll have MAI, R again, but now you'll have XT. Okay, so that's MAI, MAAR. Then you'll have MAI, then with T, RX. So like that, as we saw before, there are 6 like this, which goes on, 241 up to 246. And then it's only at the 247th one that there is a switch. Now you'll have MA. The I's would have exhausted. So then the 247th one starts with R, right? And then the very first one in the 241 is ITX. That's the alphabetical order here, ITX. And the 248th one is MAR, IXT, and so on. So you have another 6 here, right? Because you start with all those which all the different arrangements of the letters I, T, and X. They all start with MAR. So that takes me to 253, the 6. It's only the 253rd one where the R now is abandoned, and you get to the next letter, which is T. Okay? So you've got MAT. We're getting there. All right, what's the first one here? You've got MAT, you'll have to have IRX. Right? That's alphabetical order. 254 will be MAT, still starting with I, but now you'll have to have XR. Right? And that finishes the I. So the 255th one will be MAT. We finished with the I. So the next one will be R. Right, so MATR, and the first one in MATR is IX. And that's exactly the one that you're looking for. So the answer is, it's a two, the word matrix occurs 255th on this list. Quite an intricate problem, but what is important is that you must know that the number of ways in which you can arrange, a certain number of objects, like here they are letters of the alphabet, the number of ways of arranging that, if there are six n ways of n objects, then you have the number of ways of arranging it is n factorial. All the different ways in which you can write those, arrange those, if it's a word, then all the different ways in which you can write the letters, those six letters, into different words. But otherwise, you can have six objects. It doesn't have to be letters of the alphabet. You could have six people or anything, as long as they are objects, the number of ways in which you can arrange all of them. All right. So, So this now brings us to the next question, which is question 7. The diagram, I've got this diagram in the far end, the top there. It shows a commercial wind turbine with real-life dimensions used to generate electricity. So this is some kind of a windmill which generates electricity. It says that each propeller is 56 meters long. Now these are the propellers, this one here. So you can see it's 56 meters long. It goes in the form of a circle. And it goes round and round to generate electricity. In a wind speed of 54 kilometers per hour, the turbine turns at a rate of 15 revolutions per minute. In other words, in 1 minute, it goes around 15 times, right, when the wind speed is 54. Okay. They say calculate, they give you various other figures here. You know, the height of this turbine from the ground, another one here, another height, and so on, right? So they give you lots of information. Calculate the speed of the tip of the propeller blade. So this is the tip. In kilometers per hour. So that's the problem. What is the speed of the steep? It goes round and round and round. It's going quite a rapid rate if you are traveling, if it's at when the wind is at 54 kilometers per hour. Okay, so now this is really, although it makes it looks very difficult, it's not a difficult problem at all, because everything is in this one here. So the tip covers 15 revolutions. In 1 minute. So we have to translate the revolutions into distances, right? To try to get kilometers out of them. Now, one revolution, so in 1 minute, 15, it does 15 revolutions. So what is the full circumference of the circle, right? That is one revolution. So it will be 2 pi times radius. The radius of the circle. That is one revolution. Right? And the radius is given, it's 56 meters. So it's 15 times 2 pi times 56. And this is in meters. So that's in 1 minute. But now you want to know what is it in 1 hour, kilometers per hour. So it will have to be 60 minutes. This is 1 hour. So in 1 hour, which is 60 minutes, it will travel 60. Sorry. It's travel 60 times 15. I'll put 2 pi at the end. Times 56 times 2 pi. This is all in meters. All right, so if that is the case, then we have to convert this into kilometers, right? Because we've got 1 hour, it travels 16 times 15 times 56. Times 2 pi. And then That's in meters. So to get the number of kilometers, you have to divide this by 1,000 because there are 1,000 meters in a kilometer. All right, so how do you do this now? You can see, you can cancel the zeros. 5 goes into this 3 times. 5 goes into this 20 times. Okay. And 56 and 20, I can, 4 goes into this 5 times. 4 goes into this 14 times. Okay, so that's it. So you have 3 times 14 is 42, 84. 84 pi over 5. Kilometers. That's in 1 hour. Therefore, the speed is so many kilometers per hour. Okay, they say leave the answer in terms of pi. So that is the answer to this question. That's quite fast, actually. All right. So the next problem is the following. Now here you've got a kind of some funny kind of a thing here. This object here with the x and it's sort of half a bracket around it. Means the greatest integer less than or equal to x. So if x is a real number, so if you take 6,96, the greatest integer before this is 6. It's like taking off the decimals. But you have to be careful here because minus negative 573, if you plot it on the number line, then what happens is minus negative 5,73. The greatest integer less than this is negative 6 because it goes that way, see? Negative 3, negative 4. So the greatest integer less than this is negative 6. So that's how you got negative 6 here. There's a negative sign in front. And as far as 4 is concerned, it's 4 itself. All right. Okay, so now the question is, for which values of x is this true? See? So this is a tricky question because this is not an ordinary linear equation that we normally encounter. It's because this thing here has got a funny meaning. So let's just take some examples. Like for instance, if I take x to be, say, let x be equal to, say, 7, then 2x plus x. We usually call this floor. It's the one just below. There's also the other concept of the greatest integer greater than, but we are talking about the one lower. So the floor of 2x, make it x, make it 7.3. So the floor of 2x, the floor of 14.6 plus the floor of 7.3, and that gives you 14 plus 7. That's the greatest integer smaller than this, which is 21. So x equals 7.3 is not a solution because you want these two numbers to add up to 7, not to 21. These are integers, right? So you got two integers which add up to 7, and you want to know what are the values of x which will satisfy that. Okay, now the way to do this, it's a little bit advanced, but just watch the strategy. So what we do is we say, okay, we don't know what x is, but x lies between two integers. We know that x lies between two integers. Every number lies between two integers. So let's call the lower integer a. Let a be an integer such that the number x we are looking for is going to be, they say, less than or equal to x. So if x lies between two integers, I'm going to say it could be a, but not a plus 1, right? Um, every number lies between two integers, and we are including the lower integer in this thing. The reason being that whenever this happens, then we know what floor of x is. The floor of x will be the greatest integer which is smaller than or equal to a. So floor of x is actually equal to a, right? As we saw here, the floor of 696 was 6, right? Now, what about 2x now? Then 2a is less than or equal to 2x less than 2a plus 2. Now, this time, these numbers here are separated by 2 units. See? So you could have 2a, here you got 2a plus 2. And the floor of 2x, we don't know what it is because there is another number which is 2a plus 1 here in between. See? So if x was here, then the floor, I'm sorry, if 2x was here, then the floor of 2x is 2a plus 1. But if 2x was here, the floor is 2a. So this could be either 2a or 2a plus 1. That all depends on what the value of x is. In this case here, if 2x is a number here, then x is between a and a plus half. If 2x lies between 2a and 2a plus 1, then x will lie between a and a plus half. If that is the case, then the floor of 2x is 2a. Sorry, it's all squeezed up here. Okay, I'm just going to do this properly. Sorry about this. I'm going to say 2x. There are two possibilities. Either it's 2a or 2a plus 1. It's 2a if x is in the left half. And it's 2a plus 1 if x is in the right half. So this time you'll have a plus half is less than or equal to x less than. I'm sorry, it's supposed to be, yeah, is less than a plus 1. Okay, so, but now let's try to solve these equations. Now, in the first case, that means if x lies in that interval, then your 2x plus x floor of 2x plus the floor of x is equal to, in this case, it will be 2a plus the floor of x is a, right? Because in this case here, in the first case, the 2x is 2a, and that is equal to 7. But now 3a equals 7 does not give you an integer a, right? Because then a is 2 and a third. So this does not give you a solution. So it's no solution in this case. But in the second case, I'm going to just move on to this side. In the second case, you have sorry, you have the 2x plus x, floor 2x plus floor x. In this case, you have 2a plus 1, because this is the floor of 2x plus a. The floor of x is a, and that is equal to 7. And this is fine because 3a is equal to, take the one on the other side, and you have a equals 2. So there is a solution here, right? And therefore, the answer is, where is x? Hence, x lies between a and a plus half. Two plus half, which is 2.5. So so the answer is x is a number between 2 and uh, well, actually, in the first case, there was no solution. It's only in the second case there's a solution. Sorry. Sorry about this. And so what we are looking at now, here there's a solution. So x lies between a plus half and a plus 1. All right. So, so x lies between a plus half and a plus 1. And a is equal to 2. So x lies between 2.5 and 3. So if you take any number between this 2 and substitute it here and add it, you'll get 7. You can try it. See? So this is the answer to this problem. Yeah, we're gonna go out again. Uh, you may tell us, this, maybe, but I don't want to work on this. It's not usually cut. Just give it a quick, just give it and come back. We go on to question 8. It seems that I missed this one. I'm going to go back to this. Here, the problem is to determine the number of six-digit numbers that are divisible by 6 and contain 2024 in some position. So they give you 4 numbers, and the only thing is you have to find two other numbers. So the 2024 must be in exactly in its original state. But the 6-digit number is divisible by 6. So that's important, right? So we're looking for numbers which are even because they must be divisible by 6. At the same time, there must be multiples of 3. All right, so we are looking for an even number which is a multiple of 3. So let's just take, suppose the first digit is 2024. So what can we put here? Now you got 4. The last digit must be even. Okay, so it could be, the last digit could be 0, 2, 4, 6, or 8. The other thing is that they must add up to a multiple of 3. So you already got 9 here, 8. So the remaining 2 digits must be a multiple of 3 when you add them, right? So you could have, for instance, 3, 0. Wait a minute. You got 8, right? So to get a multiple of 3, the whole thing will have to add up to, say, 9. So you could have 1, 0. Right? So that's an even number, which is a multiple of 3, therefore it's a multiple of 6. But you're not allowed to put 0, 1, although it adds up to 1, because that's not an even number. So like that, now we have to count all these numbers. The 2024 need not be in the first position. It could be like this. Like that. Or you could have the first 2 numbers. The important thing is that the 2024 must be untouched. So there are 3 possibilities, where they're in the front, where in the middle, and it's at the end. Okay, so we'll come to that, but we have to take each one of them and count how many multiples of 6 do you have amongst them. All right, now, as I said here, if you got 8 already in these numbers, so 8 plus something must be a multiple of 3, right? So it could be 9 or 12 or 15 or 18 or something. These are multiples of 3. So in other words, the something that you're looking for is you have to subtract 8 from that. So you get 1 or 4, 7 plus 8 is 15, 10 plus 8 is 18, 13 plus 8 is 21, and so on. So this is the star plus star. The remaining 2 numbers, could add up to any one of these. And if they add up to any one of these, then the whole number is going to be a multiple of 3, right? So let's see now which 2 numbers add up to 1. So you're going to have, with 1, you're going to have 1, 0 or 0, 1. With 4, you could have 4, 0, 0, 4, or 3, 1, 1, 3, or 2, 2. You could have a 2, 2 as well. All right. So that's add up to 4. Now you want them to add up to 7. So you could have 0, 7, 7, 0. Or you could have 1, 6, 6, 1. Or you could have 2, 5, 5, 2. These are the possibilities for star and star plus star. 5, 2. Or you could have 6, 1. Or you could have 1, 6. Okay, I think that's as far as it goes. So you're going to have the first, if they are together, then it's like in the first 2 cases, this case and the last case, they are together. But here they are separated. It could be 1 and 6 there, for instance. All right. Okay, let's go to 10. The 2 numbers must add up to 10. So you can't have 0, 10, obviously. So it starts with 1, 9. 91, 28, 82. See, I'm making these numbers increase by ones. 82, you could have 3, 7, 7, 3, or you could 4, 6, 6, 4, or you could have 5, 5. These are only multiples of 3 now. So you've got 13, you could have had 4, 9, 9, 4, or you could have had oh, 5, 8, or 8, 5, or 8, 5, I'm sorry. Or you could have had 6, 7, 7, 6. 67, 76. Okay. Well, that's it. And then 16, you could have had 7, 9, 8, 8, or 9, 7. 19, two numbers can never add up to 19, two single digits. All right? So this is where it stops. That is why I've got this 1, 4, 7, 10, 13, 16. And here I've got the full count. How many such numbers are there? In the first case, there are 2. In the second case, there's 5. In the third one, there's 8. And in this one here, there are 9, 10. And here you have 6. And here you have 3. That's the full count of all the possible numbers which make these things divisible by 3. So, yeah. All right, now we are interested only in the even numbers, right? Because then those are multiples of 6. At the moment now, if you got these combinations, they're all multiples of 3. So you must only isolate the even numbers. So the even numbers here are that. Oh, okay, let's take each one of them separately. Let's take 2024 star star. All right, so you want the numbers to end in those two figures. So 40 is allowed, 04 is allowed, and 22 is allowed. Right? With 7, that's allowed, that's allowed, that's allowed, that's allowed. And with 10, you got that, and that, 28 and 82, 46 and 64. Those are even numbers. And 13 is 94, 58, 76. And then finally, 16 is just 88 only. So we're going to count the evens. So there's 1 in this case. You got 1, 2, 3 in the next case. Or you got 1, 2, 3, 4 in the next case. Yeah, you got 1, 2, 3, 4 again. In this case here. And here you got 1, 2, 3 in this. And the last one you got just 1. Okay, so that's the count of evens. So as far as this is concerned, you've got 4, 8, 12, 16. So there are 16 even numbers in the slot here. All right. Okay. Now, the second case is where your numbers 2024 is right in the middle. But you have to be a little bit careful here because they say it's a 6-digit number. So this number here can't be 0. See? The first number can't be 0. All right. So if you count this thing like this, you'll see there's only one first number which is 0 among the evens. See, again, it'll have to be even. Oh, sorry. The numbers are star 2024 star, single star. Sorry about this. This is a little bit. The numbers we are looking for are numbers which have the form. There's a first number. You got 2024. It's a 6-digit number. And then you have a single star here. So again, you are looking for even numbers. Not allowed to put 0. But if you look at all these underlying numbers, there's only one number which has got a 0 in front of it, and that is 0, 4. So it's all the 16, but you have to take out this number 0, comma 4 we'll put, because you can't have 0 in front. Otherwise, it's a 5-digit number. So here you've got 15 one. And in the last case, you're going to have star star 2024. In this case, the numbers end in 4 already, so all these numbers will work. You see, every one of these numbers will work. But they have to be 6-digit numbers. All right. So you got 2 plus 5 plus 7, 15, 24, 30, 33. And you have to remove all those which begin with 0. That's 1, that's 2, that's 3. There are only 3 which begin with 0. So it's 33 minus 3. So it's 30. Now notice that you can put any one of these. Yeah, it'll be a multiple of 6 because it's already a multiple of 2. So when you add up all these things, so those are the only possibilities. Therefore, the answer is 16 plus 15 plus 30, which is 61. All right, so we've taken care of all the 3 cases where 2024 appear in that order. And in each one of them, we counted the whole lot. You get the answer is 61. Okay. Okay, now we want to get on to the next problem. And that is this one. So the question is the following. 3 identical squares and a larger square are drawn as shown. You can see 3 identical and there's a larger square. And then you've got a triangle which is formed. This triangle starts from the bottom and it goes to the other end of this 3 by 1 case and it goes all the way up to that corner there. But all of them are squares. All right. So you've got a triangle and they don't give you any dimensions here. But they ask you what fraction of the total area is shaded, right, with no dimensions given. See, we can put our own dimensions there, but one has to be very careful because we don't know how this last square is constructed. All right, so what I'm going to do is I'm just going to give names to the sides. There are 2 types of squares. One has got a small square and a big square. So let's just call them, say the sides are A. The small square has got side A. And the big one, let's say, has got side B. All right, so we're going to calculate everything in terms of A and B, right? What fraction of the total area is shaded, all right? Okay, now we can work out the total area. That's easy to calculate because you got the area of these 3 squares, which is 3a squared, a squared plus a squared plus a squared, and then the big square is. So in terms of A and B, we have the total area is 3a squared plus b squared. Now the question is now, what is the shaded area? Okay. Now, you can say the shaded area is equal to half of this base. Yeah. The base for the shaded area is 2a, and the height is from the top part coming down to the bottom. So that's b. The height of the shaded triangle is b. Right? half to a, so the shaded area is really AB. Okay, so the fraction that we are looking at, the shaded area over 3a squared plus b squared. Unfortunately, that can't be the answer because you want to have a proper number. All right, so there's more to this problem than meets the eye. So we have to see if there's a relationship between A and B. See, and for that to that end, this is a little bit more advanced now. How to find the connection between A and B, right? See, A and B are not random. See, I'll tell you why. If I put a square here, if I put a very large square here, then this line here, when you take this point and extend it, right, it won't go to that corner. So you can't put any size square here. Only certain squares only. There's a very particular square which will fit inside this. Now, to that end, I'm going to do a little bit of an extra lesson here. Now, here's something. If you've got two triangles, I've got two triangles here. They're not identical. In other words, they're not congruent because I've got a small triangle and a big triangle, right? So they're not identical, but they have the same angles. You see, this triangle has got X, circle, and dot. This triangle also got X, circle, and dot. So is there anything that you can say about two triangles which have got the same angles? See? The answer is yes, you can say something about it. Because what really happens is that this triangle here is really enlargement of this triangle, right? It's as if I take a photograph of this triangle, I can get this one here. So, and a photograph of this triangle will have the same angles as the original one, but it'll be a smaller size, right? The shape is just maintained. So what does it mean? It means that all the sides are in the same proportion, right? What does it mean? It means that, like if I take A now, right? A is opposite the black dot, and R is opposite the black dot in this case. So it means that A is equal to some number, let's call it D or something. A is equal to D R. So this is a constant. The same number is going to be used in all these cases. B is equal to that thing, the D, right? Times the B is opposite cross here, and this cross here is Q. So you have that kind of a thing. Or you have C is equal to, C is opposite circle. So C is extended by the same amount. Extended, the side opposite this circle is P. So C is really corresponding to P. I've just turned these triangles around. Okay, but if you want to eliminate D, what we are saying is that A over R is D equals B over Q equals C over P. All of them are equal to D. So whenever you've got two triangles have got the same angles, there's a word for that. In grade 9, grade 11, you'll learn about this. Two triangles have got the same angles. They are said to be similar. They're not congruent, but they are similar. Right? In such a case, you have that the ratio of the sides, A over R, right, is equal to B over Q is equal to C over P. And these ratios are the same. So just bear that in mind, because I'm going to use that in this thing here. Okay. Now, what I'm going to do is to actually solve this. I'm going to give a name to this thing here. if you look at this large triangle here and this triangle, you'll see they've got the same angles. So these are corresponding angles. These lines are parallel. These are 90 degrees. And this angle is in both triangles. So these two triangles have got the same angles, which means that their corresponding sides are in the same ratio. As far as the large triangle is concerned, I've got B is one side and the other one is A plus B. But in the small triangle, I've got A, but I don't have any other side. So let me give a name to this thing here. Let's call it X. Okay. Now, according to what I've just said there, right, the ratios, let me just create some space. Right, so the ratios of the sides are the same. So you got, this is X here. The X is opposite curl in the small triangle, and the large triangle, X is opposite. What is opposite curl? It's B. So we must look at the corresponding sides. And the corresponding sides are obtained by looking at the sides which are opposite the same angle. Right? So this is X over B. Now, here, A is opposite dot. A is opposite dot. And opposite dot in the large triangle is A plus B. Right? Maybe I don't need this. Sorry. Let me just I'm not going to look at these triangles here. Sorry about this. I'm going to look at two other triangles whose sides I already know. I don't need an X. You see, this triangle here, I know this side, you see. This side is A. This side here. This is the side of the square. And this triangle here, which I'm looking at, has got the same angles as this triangle here. This line is parallel. So these angles are corresponding angles, 90 degrees, and so on. So you got this triangle here, ACF, triangle ACF. I've named them here. ACF and ACF and AEK. Have the same angles. So therefore, we can say their sides are in the same proportion. So you'll have A is opposite the corner thing there, A over B, because this thing here is opposite this angle here in the large triangle, and in the small triangle, this is opposite the dot. A over B is equal to, and now suppose we take the side here. This is opposite that one, so that is 3A, 3A, and in the large triangle, the one which is opposite that angle there, because these two angles are the same, is 3A plus B. So you have a relationship between A and B now. You see the A's can cancel. So you have 3A plus B. This one. Cross multiply is 3B. So 3A is equal to 3b minus b, which is 2b. So there is a relationship between A and B. 3 times the first one, 3A is actually equal to 2B. Or if you're like, you see they're in a certain ratio, A and B, right? A over B is actually 2 over 3. So this A is 2/3 that one. You can see it's about that. Right, so now I need to calculate this. So I'm going to go here. I know the 3A is equal to 2B. So I've got, this is the fraction that we're looking for. Why don't I create a 3A here? So this is equal to, I can create a 3A here. Let me multiply the numerator by 3, but then I have to multiply the denominator by 3 also. Why do I do that? Because then I can substitute for 3A, I can substitute 2B. Right? Now this is 3A all squared. That's nice. So that's 2B all squared. And this is 3B squared plus 3B squared. Right. And now you see it's all very nice because now you got 2B squared at the top. Bottom you got 4B squared plus 3B squared, which is 7B squared. And this is 2B all squared. So that's 2B times 2B is 4B squared. And B squareds cancel. And lo and behold, you got a nice answer. The ratio is 2 is to 7. Okay? Okay, so let us proceed now to the next problem. This is question 11. Question 11 says, a cube of side n is made up of n cubed smaller cubes. Yeah, okay, the volume of a cube is the side cubed, right? Area of base times height, which is n squared times n. So if you had, if they're all broken up into 1 by 1 cubes, then you're going to have, the number of cubes you're going to have is n cubed, right? So these are made up of all these small cubes, n cube, smaller cube. Now, some of the 6 faces of the large cube, the large cube has got 6 faces. Some of them are fully painted. So maybe those, maybe the one in front together with the top are painted, or maybe the, these 3 are painted. They say some, maybe only one of them is painted. Okay, it's a little bit complicated when these these 2 faces here are painted, because now if you want to count how many are painted, then you'll have to work out this squared. That's the number of squares which are painted here, and that squared, the n squared. So it will be 2n squared um, squares will be painted. But this corner one here, this one will be counted twice, because this thing here would have been painted. It has a face here and a face here. So you're counting the same cube twice. So if you had 2 adjacent sides, let me just say this, if 2 adjacent sides are painted, right, then total number of painted sides. Oh, yeah, no, yeah, yeah, you have to be a little careful. They say some of the 6 faces of the large cube are fully painted, and 245 smaller cubes do not have any paint on them. Now, if these 2 are painted, then there's paint here also, right? Just bear that in mind. There's paint on the top here, paint at the bottom. So you will have these n are painted, then you've got n squared plus n squared, it's 2n squared. But you are counting this particular one here, these n squares here, you're counting that twice. So you have to remove one of them, right? Are painted. squares, or cubes at least. Sorry, the writing is atrocious. And that makes life very, very complicated. But if two opposite sides are painted, then you don't have a problem. So there's no overlap. So if two opposite sides are painted, I'm just taking two. You could. I'm considering this particular one, two, for a good reason. You'll see just now. Two opposite sides are painted because they say some of them are painted. You see, I'm saying suppose two of them are painted. Then you would have that this face, for instance, this face here, all these will be painted, and the one on the other side are also painted. So you will have 2n squared are painted. They are saying 245 smaller squares have no paint on them. So how many squares don't have any paint on them? So number of cubes having no paint at all on them, the total number is n cubed, and 2n squared are painted. So you have to remove those, and those will be the number of unpainted cubes. So they've got no paint at all on them. Okay? And that is the same as n squared into n minus 2. Right? But we know how many? 245. Right? Have got no paint on them. If you factorize this thing, you get 5 times 49, and that is 7 squared times 5. And that is 7 squared into 7 minus 2. Right? So you got the same thing here, which means that what actually happened was there were two faces which were painted, and the n value is 7. So they ask you to determine the value of n. Therefore, n is equal to 7. And which faces of the large cube were fully painted, and two opposite faces. This is the only time where you have this kind of thing. Otherwise, it's very complicated. But here, this thing simplifies nicely. And n equals 7, and two opposite faces are painted. So that's the answer to this question. If you try to calculate this and say, take all the different possibilities, it's very horrendous. So the answer is in this number here, you see. When you factorize it, suddenly you see exactly what is going on. Okay, so that takes me to the next problem. And the next problem says the following. You got 1 plus 2 up to n is a 3-digit number. Prove that there is only one such 3-digit number. Now, I hope you know the formula for 1 plus 2 plus n. Everybody is supposed to know this. By the time you get to round 3, the sum of the first n natural numbers, it's a well-known formula. I'm not going to talk about it. It's n into n plus 1 over 2. Right, so you got this is n into n plus 1 over 2. If you don't believe me, you can say add 1, 2, 3, 4, 5, say maybe up to 7. When you add this all, you get 28. Right? And if you work out n, which is 7, times n plus 1, which is 8, divided by 2. 2 goes into 8 four times. So it's 7 times 4, which is 28. See? So it's very easy to add all the numbers from 1 to a certain number. Now, now they say that this is equal to a three-digit number with identical digits. All right, so suppose it's three-digit number. We'll call those identical digits, so we'll call it A. So, I mean, it could be like 111 or 222, any one of these, 999. Those are three-digit numbers with identical digits. All right. Now, this one is not a product. This is not A times A times A. It's this three-digit number. But what you can say is that this is 2 times 111. This is 9 times 111. Every one of these is something times 111. So it's A multiplied by 111, where A is that single digit. 666 is 6 times 111. Now, this is multiplication. This is a product. The other one is not. They're just digits which are left as a place next to each other. Okay, so now this is a product, just like this. So you have that I can take n into n plus 1, multiply by 2 on both sides. So you get 2a times 111. Now, this number here is the sum of the digits is 3, so 3 comes out. So this is 6a times 37. All right? So there it is. You've got the product of two consecutive numbers is equal to 6a times 37. So this number here is right next to 37 because these are consecutive numbers. It could be 38 or 36, but 38 is not of the form 6a, right? 6 does not go into 38. So 6a is actually equal to 37, 36. So this is 36 times 37, and therefore a is equal to 6. So the number you're looking at is 666. So you have 1 plus 2 plus, what is the value for n? N is this one. N is the first factor, the smaller factor. A is 6, so 6a is 36. So 1 plus 2 up to 36. You can check it out, and therefore n is 36. They say determine the value for n. So that's the solution to problem number 12. We move on to question 13. Question 13 says the following. Excuse me. Three equal-sized circles intersect with each other in such a way that each of the centers lie at a point of intersection of the other two circles. Now that's quite a handful. What we are saying here is, if you look at the diagram, either the one at the bottom or the big one here. So let's look at this. They all intersect. They are all equal circles, got the same radius. And the points of intersection, the 3 points of intersection, that each of the centers lie. So these centers, this point here is the center of the circle, this point is the center of that circle, that point is the center of the circle, the third circle. Okay, so that is how they intersect. And then you've got this nice looking shape here, which is not a triangle because the boundaries are 3 arcs. And this triangle, this looks like a triangle, it's called a Rollo triangle. I think that is how you say it, I suspect. All right. Now, the question is the following. If the area of the Rollo triangle is pi minus root 3, so we know the area of the Spink triangle, what is the radius? There's one radius. Determine the radius of the 3 circles. So that is a problem. What is the radius of these equal circles if we know the area of the triangle? So what I've done here is I've drawn this thing out. I drew the 3 triangles, but I created this triangle. Now, they said that this is the center, A is the center of that circle. So therefore, the distance from A to B will be the radius. B is on the boundary. So likewise, AC is the radius and BC is the radius of the circle here. So as far as this little triangle is concerned, if you join the 3 centers, you get an equilateral triangle, right? So you know the area of the equilateral triangle, but then there's a little piece outside this triangle, see? There are 3 pieces like that. So you got we know that pi minus root 3 is equal to the area of the triangle plus these three pieces, right? So we know what that is. So let's give a name to these things. We'll say let A be, we'll call it little a, equal to the area of the equilateral triangle. And let B be the shaded, that's one shaded area. Okay, so that means now that the area of this Rollo triangle is, let's call it R triangle, is the area of the small triangle, the equilateral triangle, which we called A, and we got 3 of these shaded areas, so it's A plus 3B. So A plus 3B we know, and that's given as pi minus root 3. It's given that the area of this triangle is pi minus root 3. All right, and now we need to find out, the question is, what is R? Now I've drawn the equilateral triangle here, having sides R. I drew a small triangle here. But if I were to draw a bigger triangle, let's hope that I can do that. And this doesn't allow me to draw a triangle, but I can. But draw a big triangle like this, equilateral. And the sides are given as R, Sides are given as R, and we know the area is A. So let us try to see whether we can calculate A in terms of R. All right. Now, the area of any triangle is half base times height. So if this is R, the A is equal to R times the height. Now, the height of the triangle, let's draw the height. The nice thing about an equilateral triangle, in fact, for any isosceles triangle, is that the height, this perpendicular, which is called the altitude, it splits the triangle into two equal parts. This happens in any any isosceles triangle, right? When you take this vertex and you draw the altitude or the perpendicular, these two triangles are identical. They are congruent. Okay, so which means that the base is then divided up into two equal parts. See? So once you draw perpendicular here, right? I needed to draw the perpendicular, so I need to calculate the area. So the area is equal to half base. Right, the base is R, so R over 2 times H. Now, the height can be calculated by using Pythagoras, right? Because you got H squared is equal to R squared minus this squared. The sum of the squares, H squared plus R over 2 all squared is R squared. So H squared itself, I need to calculate H. And that if you take out the R squared, you get 1 R squared minus a quarter R squared, which gives you 3/4 of R squared. So that is H squared. So H itself will be square root of 3 times the square root of R squared, which is R, over square root of 4, which is 2. So then eventually you have R over 2, and H is root 3 over 2 times R, and that gives you root 3. 2 times 2 is 4, and R times R is R squared. It's a very important formula. The area of a equilateral triangle is square root of 3 over 4 times the square of the side. I just remember that. That A is equal to root 3 times, well, in general, if you have a side equilateral triangle having side R, then the area of the triangle is square root of 3 over 4 times R squared. Okay, so I'm going to just remove all that because I need space. Just bear in mind that the area that we are looking for, oh, this is small a, the area of the triangle that we our triangle, we call it small a. A is the area of the equilateral triangle. Okay, so now the question is now, what is R actually equal to? Right, we've got a formula for this. So the area of this Rollo triangle we got here is pi minus root 3 plus 3b. Now, one interesting thing here is something that we can't see very easily is the following. That a plus b In other words, this triangle plus this shaded area sorry, that's quite untidy. The small shaded area plus the triangle is actually a pizza piece. It is a fraction of the area of the circle. See, this angle here is 60 degrees because it's an equilateral triangle. So you got that A plus B is actually equal to, it's a piece of the triangle, and that angle in the middle here is 60 degrees. So that is 1/6 of the area of the circle. This is a very important observation, that this piece here is 1/6 the area of the entire circle, right? Because it's only 60 degrees. And the area of the circle, we know, area of any circle of radius r is pi r squared over 6. Is pi r squared. So a plus b is pi r squared. So now you have a plus 3b is equal to this. You got a plus b is pi r squared over 6. So we can see, we can replace the a here. So let's work out the b. So the b is equal to pi r squared over 6 minus a. A plus b is this. And we know a is this. So it's pi r squared over 6 minus a is √3 over 4 times r squared. Now that is b. Okay? So what do we have? We have the pi minus √3 is a plus 3b. So a is √3 over √3 r squared over 4. And 3b, this b is this, 3b is 3 times this. So it's 3 times this, which is 3 pi r squared over 6 minus 3 √3 over 4 r squared. Okay, so if you work out all this, when you add these two, yeah, so this part here is pi r squared over 2. Pi r squared over 2, this part here. And this part is a quarter of 3 √3 r squared minus 3/4 of √3 r squared. So that'll be minus half √3 r squared. Okay, so it's quarter minus 3/4 is minus half. So if you look at this nicely, you see the r squared. If you multiply this by 2 on both sides, you get, sorry, I'm running out of space here. So let me just squeeze into the space. I don't need too much of space. Sorry for the untidiness. So you got a 2 at the bottom here, and you got this. So if I multiply this both sides by 2, I'll have pi r squared minus √3 r squared. So r squared comes out as a common factor. And the other factor is pi minus √3, happily. Right? Because r squared, pi r squared minus √3 r squared is, so the pi minus √3 cancels. And lo and behold, you have r squared is equal to 2, so that r is equal to square root of 2. See, so r squared is equal to 2. So the radius that we are looking for is the square root of 2. Okay, so that is quite a challenging problem there, uh, like many of these problems. So let's get on to the very last problem that we want to do. Well, actually, it's the second last problem. Before that, I just want to go to the last problem because the second last problem is quite demanding. It takes some time. So let me get to the very last problem, which is the following. This is an interesting problem. It says here, a slab of chocolate has dimensions 8 blocks by 5 blocks. The slab is drawn at the bottom here. So you can imagine this is a slab of chocolate. And it's got all these 40 pieces of it, so many people can share it. Okay, now a game is played by 2 players. Right, so you got 2 players, a player 1 and a player 2. Now, so you got 2 players. So what do they do? Taking turns, each player breaks off a number of columns or a number of rows. So a player can take out an entire column like this, or you can take out an entire row. So that's what each player can do, right? And you can take out any number. It doesn't really matter. You can take out any number of columns or any number of rows. Now, the player who takes the last piece of any size loses, right? Now, is there a strategy that will ensure a win for either player? Motivate your answer clearly. So now let's just see now the player who takes the very last piece loses. All right. So let me just let me get to a situation like this. Suppose, okay, before that, so if I suppose I'm playing you, all right, and I leave you with this single square, then you lose because you have to take that one away. All right. So I have to leave you with a single square because if I leave you with any other square, if I leave you with say a 2 by 1, like that, then you will win because you will take out you're allowed to take out any row, you see. So you'll take out the top row and then you leave me with this. So I'm sitting with 1 and I lose. Okay. So I can't leave you with that. In fact, if you look at it carefully, you'll see that even if you but if I leave you with a square of some size like this, suppose I leave you with a square, a 2 by 2 square. Suppose I leave you with the 2 by 2 square like this. Then I will win because you have to lop off a row, right? Which will lead to that, or a column which will still lead to that, right? So you will have to give me that, and then if you give me that, I will win because I will take out that one of those pieces and I'll leave you with a single square. So the lesson is if I leave you with a 1 by 1, you lose. If I leave you with a 2 by 2, you lose. In fact, if I leave you with any grid, which is R by R, then you lose. You see? Because what will happen is if you have if I leave you with a, for instance, if I leave you with a 3 by 3, if I leave you with the 3 by 3, oh, sorry. Okay, suppose I leave you with the 5 by 5. As long as I leave you with the square, then no matter what you do, if you lop off these, the first two rows, right, then I will lop off the two columns and I'll leave you with a square. See? If you lop off two rows, I will lop off two columns. If you lop off two columns, I'll lop off two rows. So I will always leave you with a smaller square. And it'll keep coming down like that until you come down to a situation like this and that, and therefore I win. So the strategy is, the winning strategy is I will always have to leave you with a square. So in this particular case, in the 5 by 8 one, I'll simply, you got 5 by 8, so I'll lop off three columns, right? I'll lop off three columns and I'll leave you with a 5 by 5 square like this. And then as we saw, this will eventually lead to my win. So the strategy is I take off, I will always create a smaller rectangle, which is a square. See, I'll create a 5 by 5 rectangle. From a 5 by 8, I'll create a 5 by 5 square. So the second part says if you got a chocolate dimensions X blocks by Y blocks, what is the winning strategy? It's easy. All you have to do is to lop off, uh, if X is equal to Y, oh yes, if X is equal to Y, then I am left with a square. Then you will win. But if X is not equal to Y, then you've got a proper rectangle, then I will win because I will just lop off some of those columns or rows, depending on the size, and I'll leave you with a square. As long as I leave you with a square, you lose. All right, so that is the winning strategy for this. It takes a long time to finally decide on the winning strategy, but that's how it goes. These are all problem solving, quite tricky problem solving. Okay, so that was question 15 actually. And the question that I left out, I'm going to do now, is question 14. Okay, so just ignore those two diagrams there. Let's read the question. A racetrack with circular bends of equal radii is shown. All right, now that needs a little bit of understanding. The circular bends of equal radii are shown. So what happens is that this bend here is a circular bend, and these are equal radii. So there's a circle. The bends are part of a circle. They all got equal radii. Right? So if the center of the circles are like that, and if I draw the circle, the center is really offbeat here a little bit. Okay, here I've got it. So this A here is the center of that circle, and B is the center of that circle. So these are of equal radii. The smaller one also is a circle. So you got two circles actually, and they're concentric circles. Why? Because they say that the inside perimeter of the racetrack, the width is a constant. So in other words, all these are constant width. So there must be these two circles here. If you draw the circles out fully, then these are concentric circles. Okay. Now, what's interesting is that I just want to take out this. And I have to admit that I didn't see it myself. Okay, before I get to that, let's continue with the question. The inside perimeter of the racetrack is 20 meters. So in other words, this part here remove all this. If I go right round the inside, this full length here is 20 meters, and the full length of the outside is 24 meters. All right. Then they ask you, what is the area of the racetrack? Okay, this is not an easy problem, and I'm going to take a little bit of a while with this. You need to find out the area which is shaded here. Okay, and to do that, I've created a much more complicated kind of a picture here. Right? We need to calculate the area of the racetrack. But before we calculate the area, I just want to show you something. You see, this is the center of this of these circular parts, and so is B and so is C. Right. Now you've got three similar kinds of things, but they need not be the same size. You can see this one here has got a small size, and that one's got a very big size, and this was something which is in between, right? Now, the key observation here is, you see, when you want to work out the perimeter, the outside perimeter, right? The way to do that is to complete this thing wherever the circle ends. The circle will end here somewhere, and then you have the straight. And here the circle starts, then you have a straight, and here you have the circle. Remember, it's a racetrack, and circle, and then you have straight. So let's call the straights A, B, and C, as I have done. And then what I did was drawn this to show the actual circle from the center of the circle. I go up to this point where the straight starts, right? So you can see, because this is like a tangent here, this thing here is a tangent to that circle. So you'll have that this thing is actually 90 degrees here, like that. See? When you take the center and you join it to the tangent, to a circle, 90 degrees. I think that's kind of pretty obvious when you come up to that. So what happens is that you have that all these things are rectangles here. See? These three pieces here are rectangles. Okay. Now, these three pizza pies, this large part here, and this part, and this part, if you put them together, you will get a circle. What I've done here is I've taken this piece, I put it in here. Taken this piece and put it in. Actually, it's a little bit skewed. Okay, I've taken this piece and put it in here, and then this one. Then you'll see that they all fit nicely. I can take this, slide it along this, right? And then you'll get a larger piece, and then this thing fits snugly into that. Now, how do I know that? That's not obvious at all. Okay? To prove that, you have to take this angle alpha, which is the angle of this sector here, and add it to beta, which is the angle in the middle of this sector, and add it to gamma. And when you work it out, you'll see that it's actually equal to 360 degrees. And that is how, if alpha and beta and gamma, the last piece will fit in exactly. Right. And how do you know it's 360 degrees? You can calculate it. You see? I'm not going to go into the details, but If you add, here you got 180 degrees, 90, 90, and A. So at A, you have, at A, you've got alpha plus 180 degrees plus angle A. The angle A I'm talking about is this one here, the internal angle. So the internal angle plus these two 90 degrees, remember these are rectangles, plus alpha is the whole angle at A, so that is 360 degrees. See? And you have a similar thing for beta. But there you have angle B. It's also 360 degrees. And then you have gamma. We are working out the sum total of all the angles at each of those points, right? And then, now this is what I claim. I claim that alpha plus beta is 360. Now, when you add all these three, and bearing in mind that angle A plus B plus C are the angles of a triangle. So A plus B plus C is 180 degrees, right? Do the calculations, and you will see that alpha plus beta plus gamma is 360. And that guarantees that when I slide this to meet this, this will fit in exactly. Now, why do we need all that? Because the reason for that is, I'm going to take out all this because I need space. Because I need to have a formula to say the outside perimeter. The outside perimeter, okay, this, okay, the outside perimeter is what? Well, if you go right round, it is these three straights A plus B plus C. This is the outside perimeter I'm calculating. These three straights plus this curve, outside curve, plus this curve here, outside curve, plus this curve here, right? In other words, it's the circumference of the outside circle, because we said those three meet. So this is equal to the circumference, the outside circumference. I'll put large, the large circle, and that is 24, right? Now, we know the outside circumference of the large circle because I didn't give a name to this, but this distance, this fixed distance, the width, right, is constant. We give a name to that. Let's call it D. So D is this distance here from here to here. So therefore, the radius of the outside circle is R plus D. So you got A plus B plus C. The radius of the outside circle is R plus D. So therefore, its circumference is 2 pi into R plus D, and that is equal to 24. And remember, we're trying to calculate this area here. It's a long way to get there. Likewise, the inside perimeter is still A plus B plus C, because you're going to add these three, which are still the same thing, plus the inside circumference, right? So it's this part, plus that part, which gives you the inside circumference. And the inside circumference is, the radius of the inside one is small r, so it's 2 pi r, and that is 20. It was given that the inside perimeter is 20, and the outside is 24. Okay, so you got these two equations here. And if you subtract these two equations, many of them will just cancel off, because the 2 pi r will cancel off with this. And you get 2 pi r times d. That's what you get left here. The 2 pi r will cancel off. Is 24 minus 20, which is 4, which gives you a very nice formula, which is pi r d is equal to 4, 2 at least. I'll just hold on with that. Oh, I'm sorry, it's actually 2 pi d. The r's cancel. So when you expand this, you get 2 pi r plus 2 pi d. There's no r there, which is very nice. So you got 2 pi d is 4. Okay, so let's just hold on with that. That tells you what d is. The distance between these two is 4 divided by 2 pi, which is very nice. All right, so now we know this part here. We know that this is 4 divided by 2 pi. And the area of this, the shaded area that you're looking for is the area of the three rectangles. Okay, let's take that area plus this area. Let's do the rectangles first because it's easy to calculate the area of the rectangle, right? Is length times breadth, which is AD, plus this other one, which is BD, plus CD. That's the area of this rectangle, C times D. So that's the area, one part of the area of the shaded triangle. And then the shaded triangle has also got this area here. I mean, the shaded area, it's that piece, plus that piece, plus that piece. So this gives you the thing that we're looking for is the black area plus the area of these three red pieces. But as we saw now, the area of the three red pieces is exactly, this piece here is that one, plus that one, plus that one. So the area of the red piece is the area of this ring inside here. And the area of that ring is the area of the large circle. The area of the large circle, which is pi into r plus d all squared. That is how you calculate the area of a circle. It's pi times radius squared minus the area of the small circle, right, which is pi r squared, and that will give you the red area. Right, so this is the black area plus the red area is equal to the shaded area. This is what we need to calculate. So this is d into a plus b plus c. It looks as if we'll never get anywhere because all these are unknowns. Right? Now this part here is, if you expand this, you got pi, the square of a binomial is r squared plus 2dr plus d squared. So this part here is r squared plus 2dr plus r squared. I got a pi outside, so let me multiply all these. Pi r squared plus 2 pi dr, 2 pi dr plus pi d squared. Now that's just this part here. And then you are going to subtract from that pi r squared. So these cancel. And then, as far as those two are concerned, this is d into a plus b plus c. Take out d. There's a d as a common factor here, plus 2 pi r. So those two are that. And then you got a pi d squared plus pi d squared. I'm taking out d as a common factor between these two. And watch, a plus b plus c plus 2 pi r is 20. We know this thing here. Really beautiful. This rather horrible object here, with all these unknowns, we know this whole thing here is 20. So this is 20d plus pi d squared, right? 20d plus pi d squared. Now we know what pi d is. Pi d is 2. Pi d is 2. So 20d, if you take out one of the d's here, pi d is 2, and it'll be 2d. But now you have 22d. But we even know d, because d, pi times d is 2, so d is 2 over pi. So 22 times 2 over pi is 44 over pi. A very beautiful problem, where you can calculate the area of the track exactly only by knowing what the outside perimeter is and what the inside perimeter is. Right? And the area is 44 over pi. You know what pi is, 3 and 1/7. So you've got exactly what the shaded area is. Okay, so thank you very much for listening. And that brings now us to the end of this rather long session. Thank you very much and have a good day or a good evening.